Welcome to this explainer. Today, we're diving right into the state design pattern in Go, and we're gonna explore exactly how it takes messy, bug-prone conditional trees and magically turns them into elegant, finite state machines.
To really appreciate this pattern, we have to feel the pain it solves. Think about a typical order ship method in your codebase. It's probably filled with, what, 6 nested if-else blocks, handling everything from a pending state all the way down to delivered. But here's the really scary question. What happens when we add a 7th state, an 8th? What if the business suddenly demands a disputed state? Suddenly, that simple shipping method explodes into a monstrous, fragile wall of logic where one tiny typo brings down the entire system.
Section 1. The conditional explosion problem. Why our life cycles become maintenance nightmares. So, the naive way to handle life cycles is stuffing massive conditional trees into every single method. It starts out as a quick fix, right? But 3 months later, it's a terrifying reality. Just one missed else if in that giant stack doesn't just throw a benign error, it creates a critical, system-wide bug that might actually let you ship an order that was already delivered. We have got to replace this explosion of conditionals with self-contained state types. By doing this, each state only knows about its own valid transitions. A bug in one isolated step simply can't leak out and destroy the rest of your application. Section 2. Visualizing state machines. The shape of the architecture before the code.
Now, before we look at a single line of Go code, we have to draw out the state transition diagram. It's absolutely crucial to let you see the shape of the solution before the implementation. We start at, well, the start state, which naturally moves directly to the AskState. Now, the AskState is where it gets interesting. It transitions to itself to create a loop, or it moves on to the FinishState. Finally, the FinishState does the routing to either a WinState or a LoseState. That's the whole blueprint. Notice how no single state cares about the global picture. They only care about their immediate neighbors.
Section 3. Go implementation and mechanics. Interfaces and contexts. To actually build this blueprint in Go, we just need 2 core pieces. First, a lean game context struct. We pass this around by pointer so any mutations are instantly visible across all our states. It's kind of like a shared whiteboard that holds our data, plus a super important pointer to the next state. Second, we have a wonderfully simple state interface. It dictates execution through just one function, execute state. Every isolated state we just mapped out is going to implement this exact interface.
And here it is, the absolute aha moment of this entire explainer. For game.next.executeState and game. Just look at that. That is a full, finite state machine engine running continuously inside one single beautiful line of Go. There is not a single switch statement in sight. The active state object completely drives the logic, updates the next state on the context, and returns true to keep the loop spinning. The pure elegance of this is the ultimate payoff. Section 4. Live tracing the engine, animating the execution path. To really make this click, let's walk through our game FSM state by state. We initialize right at the start state, which sets things up and passes the baton. Then we drop into our main game loop in the ask state. We go ask again as it loops back on itself handling user input. When the loop finally breaks, it hands off to the finish state, which inspects our context and smoothly routes us into our terminal WinState. It is completely seamless.
Section 5. Extending without breaking. Safely adding new features.
Now, the real superpower of this pattern hits when the business requirements inevitably change. Let's say we originally just printed a basic game over message, but now we need to add complex WinState and LoseState sequences as a refactor. Because of our architecture, we're extending the FSM without touching any existing state logic. We literally just drop in the new structs, update one routing transition in the finish state, and we're done. 0 modifications required in the start or ask states.
Section 6. Real-world deployments and constraints, from cheating to best practices.
You might be wondering where this actually gets used out in the wild. Well, everyone in the audience has used TCP today, right? But I bet practically none of us have thought about its FSM nature. Mapping it out reveals TCP is basically a formalized state pattern transitioning from closed to SYN_sent to established. You also see this pattern orchestrating order management systems, dictating game AI so a guard flawlessly shifts from patrol to chase, and powering complex workflow automations. It's everywhere.
But let's be real, you shouldn't use this for absolutely everything. If you only have 2 or 3 states with really basic Boolean flags, just use an if statement. Keep it simple. Also, if you have extremely high-frequency transitions, creating all these isolated structs might actually cause Go garbage collection pressure, making it overkill. And whatever you do, please don't fall for the stringly typed anti-pattern, where you just pass state around as raw strings and parse them with giant switch blocks. That defeats the whole purpose.
Now, I want to leave you with a massive operational insight. Are you ready? In production, a state machine without a transition log is a black box, period. You absolutely must ensure that your context logs every single state transition. If you don't, and an order gets stuck somewhere out in the ether, you have literally deployed an undebuggable system. Always log the transitions. So to wrap this explainer up, I want you to remember this. Every complex workflow in your system is a state machine, whether you formalized it or not. The state pattern just makes it explicit. So take a look at the codebase you're working in today. Which fragile, messy conditional tree is secretly begging to be transformed into an elegant, explicit state machine? Tame the explosion and write code you'll actually enjoy maintaining. Thanks for joining me, and I'll catch you on the next one.